in the quantum field thanks to COVID. Sorry, very sad about COVID, of course, but like I also like have been seeing that a lot of labs have been able to operate at higher capacity in terms of quantum work because they're able to actually work without as many interactions ruining their experiments. And thanks to the software being available now, and people are able to have the chance to look at them. I think the quantum software world has definitely increased dramatically over the last like 6 months. So very, very exciting time to be in this field, and hope that one of us to here today goes to make something that changes the way our world operates using these quantum technologies.
Yeah, Samarth makes an excellent case. There's been a great deal of more research into the applications of quantum computing for for simulating a lot of biological processes, and considering the fact that problems like the whole reason that quantum computers even exist was started off as like a kind of fanciful idea from Richard Feynman, who was complaining, or he knew that it's pretty hard for computers to solve those differential equations. In fact, I think that's a perfect starting point. I'll go ahead and get my side of things started. Let me go ahead and share my screen. I will have chat open. So if there are any questions, I can see them to one of my monitors, and I'll try and respond to them as soon as possible. So with that being said, let's go ahead and share my screen. I will start with Microsoft OneNote. Here we go. Okay. No, this is not related to what we're doing today. This is just a bit of a circuits-related homework. So let's see. I'll open up the chat, and I can see everything here along with any. Okay, cool. So yeah, Samarth was talking about how COVID is a terrible thing, yes, but at the same time, it spurred a lot of innovation, because a lot of people are finding out or are motivated to use quantum computers to perform a lot of the computation required for many molecular simulations, and protein folding. Protein folding is one of those problems that are inherently difficult for a classical computer to do. And part of it is it's not so much that differential equations are hard to solve. So if you remember from my earlier meetings, I went through a great deal over the Schrodinger wave equation, which is the sort of fundamental crux of quantum mechanics. And it is a second order linear differential equation. Basically the wave function that I talked about, let's change the color here. There we go. The wave function that I mentioned in the very beginning, it takes some component of space and some component of time. And for this, for many of the examples you find in academia, we always love to start in a singular dimension, so we confine our particle to a singular x-axis. Although the reality is, if you're doing molecular simulations, this wave function will generally expand to maybe x, y, and z. Although it's rare to use these rectangular coordinates because the polar coordinates are much better. Of course, if you use the polar coordinates, then your method of defining the second order derivatives has to change through the Laplacian, I believe. But with that being said, these wave functions don't live by themselves. They're always embedded in that differential equation. You have to remember that for differential equations, the solution to a differential equation is that you will get some resulting function, f of x. So this is, if you learn from algebra, like, okay, I'm going to solve this equation, I will get some integer or some floating point value. Then you take the next step where it's like, oh, you have these equations now where the answer itself is a function. And in the case of the Schrodinger wave equation, then your function is essentially the wave function. And we remember that the wave function describes everything we could ever want to know about a wave. Of course, that information isn't apparent because the output of this wave function is always going to be complex value, a plus bi. And the motivation for doing this, part of the beauty of working with complex numbers is how much information that they can represent in their compact format. Like just with this kind of combination, I could represent, in polar coordinates, I can represent a magnitude as well as an angle. And in quantum mechanics, especially, we have to find a way to pack a lot of information into one value. So we will end up using this sort of complex valued output. With that being said, going back to what Samarth was saying, I know I immediately kind of cut off Samarth there because I thought it was a great entry point into one of the motivations for quantum computing, which is that dealing with these wave functions is a very painful thing to do, especially when, like maybe if I have like a carbon atom and another carbon atom, like this is a trivial thing to simulate. I could do this on my laptop. But as I keep adding, more atoms and bonds and molecules, you have to remember that these aren't just, individual sort of spheres with a stick holding them. They have a bunch of sort of interatomic forces. There's entanglement that goes on in certain molecules as well. And this becomes exponentially difficult for modern supercomputers to simulate. So I think it was Richard Feynman who came up with the idea saying, hey, why don't we instead use a system that is inherently quantum to simulate quantum mechanics. And in the early 90s, you started to see some real research with ion traps. And you will remember that with any quantum computing system, one of the beautiful things about it is the nature of that quantum system you can play a little loose with it. Because for quantum computing to occur, I've always sort of cited two criteria. You need to have superposition. So I should be able to have some arbitrary combination. Oh, whoops, that is improper notation. If you see someone writing notation like that, they are not an actual physicist or quantum computing enthusiast. So I usually have some superposition of two states. So these are my two quantum states. And then alpha and beta here are the sort of coefficients. And these coefficients have to, if I were to take if I were to do this, they should add up to 1. And this is part of this requirement here. It comes from the normalization criteria, because if you remember from the last workshop, I mentioned that these are sort of these are really vectors. Like this is just another notation for vectors, and we take advantage of an idea in linear algebra. So I can take my sort of wave functions, psi x of t, or those differential equations, or those operators. And operators are sort of like they're sort of like dangling functions almost. And through Hilbert space, so through the Hilbert space, these can now become vectors. So I can represent certain eigenstates or eigenvalues as their own vectors, or in this case, this would become a matrix. So if this is some vector like 0, 1, then our operators now become entire matrices. And as you know, it's far easier to deal with linear algebra than it is to work in the realm of these infinitely continuous wave functions and operators. So we take advantage of an idea from linear algebra, these spaces, to get to vectors and matrices. And with that idea in place, like with this mathematical abstraction, then we can really play loose with some of these quantum mechanical ideas for quantum computing, these criteria for quantum computing, because I mentioned that, there we go, that looks much better. I mentioned that, okay, this is one of the criteria. We need this superposition, and then we also will need some form of entanglement. And entanglement is just the idea that if I have two sort of quantum systems, they can be linked in some kind of some fashion, so that the behavior of one will instantaneously affect the behavior of the other. Now, I won't go over the exact proof. Like if you think, like I mentioned the word instantaneous, and you will intuitively believe that there is some way to perform faster than light communication, even though Einstein and many other physicists have proven that light is sort of the speed of light is the fundamental barrier in the physics universe. You can't go faster than the speed of light without violating certain rules. So with entanglement, yes, if regardless of where this quantum system is from this quantum system, anywhere in space, there will be some kind of change. But you can't use this property to perform any real direct communication. So I don't know how many of you are science fiction fans, but like Isaac Asimov's Foundation series, there's a talk of the hyper relay, where I can be like 10 million light years away from you, and I can send you a message just like that. And the story goes they might be entangled, but you can't do that. And it's just another limitation of physics. But I digress. Entanglement is one of those super cool features that it's very easy to get lost in. But these two criteria you will need for any quantum computer. You'll need a superposition and you'll need entanglement. Now, inherently, when we think of the word sort of quantum, we're biased towards believing that, okay, well, quantum means very, very small. So small that maybe we're just dealing with a single particle, like our fellow electron here. Or, but the reality is, you can take advantage of any other systems that exhibit quantum properties. So the reality is that yes, we can use individual particles, subatomic particles, to perform quantum computation. But most of the time, like for ion trap systems, we have some kind of ion. So the ion will definitely still have like a nucleus, and we'll still have some electrons floating around. So this is a larger quantum system, but in our intuition, it's still quantum, right? Because it's just a bunch of subatomic particles kind of lumped together, and it is very small. But then it becomes a little harder to understand, because if you look at what IBM, what Rigetti, and some of the other companies are doing out there, D-Wave, Fujitsu, they are using superconducting silicon. And silicon, their qubits contain thousands, if not tens of thousands or millions of atoms of silicon. And that's when our intuition kind of breaks down, and we think, wait a minute, why is that still considered quantum computing if the system itself is macroscopic? If it's that big, how can it still exhibit quantum phenomena? And it can. And I think in the last workshop, I went over an explanation of that. But I'll hold off on it now, because I want to get to singular gates. And I know I'm going in a bit of a very circuitous fashion in explaining things, but I just want to emphasize once again that what exactly you use in your quantum computer is very sort of open to you, as long as it exhibits superposition and this property of entanglement. Because the wave function, or the Schrodinger wave equation, there is no, the Schrodinger wave equation doesn't have some kind of, footnote. It doesn't have an asterisk saying like, oh, P.S., you can only use this for single atoms, or you can only use this for subatomic particles. In reality, you can define a wave function for certain, for larger systems. And more importantly, is you want to look at the Hamiltonian of a certain system. So the Hamiltonian is just the sum of your kinetic and potential energies. Kinetic energy and the potential energy. This is one way of doing it. You can define custom energy landscapes, like here. Here is a common, this is the sort of energy well, or where your quantum system has a pullback force. It's almost the equivalent of a spring and a ball. And this is the abstracted notation. This is just the Hamiltonian. I'm just describing the energy landscape here. The difference between the potential energy. I'm just sort of mapping out the potential energies here. And in quantum systems, we know that you can only occupy certain energy eigenstates, or very specific energy levels. Now, as a result of that, I said, for a quantum system to work, we need superposition, right? Well, you can have a superposition of energy levels. That's a very common thing to see in quantum mechanics. In fact, that's exactly what superconducting silicon systems use. Is they take some energy levels and they will use them to satisfy this criteria of superposition. But I mentioned ion trapping. So what is this idea behind ion trapping? Well, I can have some ion, and you have to remember that an ion is not a poorly illustrated spaghetti ball. Ball of spaghetti? Meatball, sorry. Oh, good heavens. You have to pardon my lapse in thinking there. But yeah, an ion is not a poorly illustrated meatball, but it is in fact an atom. It's an atom missing, or having added a certain number of electrons. And we constrain this nucleus and its surrounding electrons inside of an electromagnetic field. And we could use specialized radio frequency pulses to kind of tune the particle's spin. So spin is another quantum property. Spin does have a Hamiltonian, but spin is just another quantum property that you can also do superposition with, because you can have particles and spin up and spin down. And this is also a quantized property. So there's no such thing as spin something like that, or it takes on discrete levels. So there's no like infinite continuation. You can also use photon polarization. So photons can be vertically or horizontally polarized, and you can also get a superposition there. So what I'm trying to get at here is your superposition does not necessarily just need to be energy levels, or, for all that matters, individual atoms or nuclei. Like in some quantum systems will use like a NMR-based nuclear magnetic resonance systems. But you can also use any other quantum property that has discrete values. So you, for the purposes of simplicity, I'm saying you can't use something that has an infinitely continuous energy levels. But if you look up what Xanadu does, Xanadu is another quantum computing company. They use photonic-based quantum computing. They do have something along the lines of a continuous variant system instead of these quantized energy levels. But the catch or the caveat is that Xanadu does not use the same sort of gate logic that this whole course that I've built, or not course, but these workshops that I built are intended to teach you. Xanadu uses Gaussian boson sampling, which is, how do I put this? I mentioned quantum computing. So for all forms of quantum computing, you will need, entanglement and superposition, yes. But the way about which you express your problem in a quantum mechanical fashion and the way in which you solve it can vary drastically. Like, for example, D-Wave in Canada, or in Vancouver, they focus on AQC. AQC is considered adiabatic quantum computation. And AQC is radically different from what I showed you in the last workshop, where I'm like, okay, so in the last workshop we have the gate model, which is very easy to understand. I have this vector represents my qubit state, and I'm going to feed it through a number of these gates, like a Hadamard or a NOT gate, and then in the end, some transformation has occurred to my state vector, and I will get a result that's either 1 or 0, because you have to remember that the moment you perform a measurement, you will lose your inherent quantum properties. So this is the gate model, and there are a lot of algorithms in existence for the gate model, but and it is quantum in nature. But AQC is simply another way of performing computation, but it doesn't use the gates. So both of these still need qubits that exhibit superposition and entanglement, but you can express your problem in radically different ways. The basic idea behind AQC is that I have to express my problem in terms of a Hamiltonian. So I will, maybe there's some kind of problem I can find, and then I express it in terms of an energy landscape. So you have to remember that we like to illustrate, or I like to illustrate Hamiltonians through this kind of energy landscape. And we encode our Hamiltonian, our sum of kinetic and potential energies, in such a way that the minima of my Hamiltonian represent some ideal solution. And the idea behind this ideal solution is that normally it's very difficult to find a solution like this. And you'll notice that I'm drawing this. This is sort of like a one-dimensional representation. But there are problems with finance and with optimization that have millions, if not millions of variables. And I would have an n-dimensional chart here with this very complicated terrain and topology, and I would have to somehow find these minima. So the idea with adiabatic quantum computation is I can start with an arbitrary, a very simple Hamiltonian, and I ever so slowly evolve towards this more complicated Hamiltonian. And by doing it slowly, that's where the adiabatic comes from, I can find, or I can stay within these minima. Now, why is it that we don't hear more about adiabatic quantum computation? Why has the gate model sort of dominated the quantum computing scene? Well, the gate model is a lot more universal in what it can accomplish. Although there is mathematical proof that these two models are technically equivalent. I believe there's a proof that was published in I think some Chinese researchers. If I can, I'll try and send the link out in the next email. It's a very, very hard read. A lot of the math even goes over my head. But the basic idea is that if I have a problem in a gate model, it'll take me a polynomial amount of time to convert it or no, it's the other way around. If I have a problem that's expressible as a Hamiltonian, it takes me some polynomial time to convert it into something the gates can solve. And the discrepancy between their execution speeds could also be reduced to a polynomial. So that is, yeah, that's just an equivalence model. But I digress. This whole detour that I just took is just to tell you guys that quantum computing is not just gates. It is not just silicon or superconducting silicon or photons. There are a myriad of methods out there, and all those methods are vying for supremacy. So the way I want you guys to think of quantum computing now is, if you look back in history, and you guys all know the infamous saying that those that do not learn from history are doomed to repeat it. And history does repeat itself, because somewhere in the, I would say from the 60s to the 70s, the personal computer market was just getting started, and you had, I think there were, upwards of 25 plus companies building personal computers. And now, if you look at the market now, it's just what, IBM, Hewlett Packard, maybe I could count them on a single hand probably. And the reason being is that, market competition will show certain architectures or certain designs are less are worse or harder to work with than others, or some are simply just unsuited for our needs. So in the case of quantum computing, we're still trying to figure out what exactly, which model is really good for us, and which models we don't want, and or are not really as performant as we'd like them to be. And you might be wondering, like, well, if the gate model is, as I use this word, more universal, because there's a lot more you can technically do on a gate model than you can do with the adiabatic model, then why is it that D-Wave still exists? Why do companies like Fujitsu and D-Wave still bother with this adiabatic model? Well, it's part of it is scalability. So there are a number of desirable criteria we want from a quantum computer. I highly encourage you to check out DiVincenzo's criteria. DiVincenzo. I really hope he, you'll forgive me for that little typo there, but DiVincenzo's criteria, and these criteria describe what an actual usable quantum computer should have. And part of the things with with qubits is qubits are prone to error, very prone to error. Like, imagine if the computer or cell phone you're using right now, imagine if, like, within 1 second the 0 became a 1 or a 1 became a 0, and you would think, wow, that's terrible. Like, how can you get anything useful done? And the trick is you either have to perform your computations very quickly, or you have to find a qubit that lasts longer, because one of the issues we always deal with is decoherence. And decoherence is the idea that I can be in some quantum state. So, if I were to draw the block sphere again, I'm living in my superposition, and I have some phase, but maybe some external interference, like electromagnetic radiation, or perhaps you decided to put your coffee mug on top of a Rigetti quantum computer. Even that thermal heat is enough to disrupt operations, and as a result, your qubits will start to flip, and they will lose their quantum properties. So, with all these different models of computation, or more specifically, all the different models of qubits that are possible, we are trying to find qubits that either live very long, or you can perform operations very quickly, or more importantly is the idea of scalability. So part of the reason why that ion trap method I mentioned, so you have some ions, like, oh, here are my little ions, they're constrained in this kind of magnetic field. And this isn't a static magnetic field. In fact, I think there's proof that if you have charges in 3 dimensions, you can't constrain them with a static field. The field has some kind of alternating current going through it. So I can have a line of ions, and I can use some sort of RF frequency to adjust their spins and whatnot. The great thing with ion trapping is that the qubits live for very long times. This is wonderful. But the rather terrible thing about ion trapping is it takes a really, like, it's not particularly scalable, because the amount of additional hardware I have to keep adding to add more ions is rather prohibitive. So this is where kind of the adiabatic model kind of shines. If you look at D-Wave statistics, I I think they're up to 2,000 qubits now, which seems very cool until you realize they're 2,000 qubits that only use the adiabatic method. So you really have to think hard as to how you can take your problem and convert it into some kind of Hamiltonian. And most of the time, not every problem in life is translatable to a Hamiltonian. Oh, okay. So Samarth says that okay, they managed to double this. Okay, so yeah, D-Wave's been there's a lot of qubits that are particularly it's very easy for them to scale up their hardware, but D-Wave still suffers from I believe they have shorter lifespans than ion trapped qubits, and you can just from all this stuff I keep telling you about with these different platforms like D-Wave and ion trapping. If you want to check out ion trapping, by the way, I think your go-tos would be IonQ and Honeywell. Honeywell having just released one of their it's sort of their first foray into quantum computing. But they do have a rather powerful computer that has garnered a lot of interest. But yeah, it's just right now there are all these startups, all these companies that are really like competing in this race to build a truly scalable quantum computer with long-lasting qubits, operations that are quick, and all of the above. And even with these sort of short-lived qubits, there are some workarounds. Qubits can't really last forever. There's always going to be some kind of decoherence time. So one of the workarounds to that is error correction. But we use quantum error correction. And it's always been my goal in one of these workshops to really show you guys how that error correction works. And there are a number of really simple systems. Like the simplest one would be the sort of redundancy code, which is where let's say I want to work or manipulate with two qubits. Then I have to add an external qubit that is kind of here to monitor these other two qubits. So if something goes awry, and this qubit for some some error happens, that Rigetti intern decided to put his coffee mug on your computer and the qubit loses its quantum state, then we'll have to you can use this qubit. You can use this qubit to figure out, holy smokes, something bad happened, and we can correct that error. So we can kind of buy ourselves a little more time. So there is a great deal of research into this kind of error correction technology, or in fact, implementing firmware directly into quantum computers that will obscure. It'll do the error correction without you having to intervene or bother with it, which is great. That's a company called Q Control. You can check it out if you're particularly interested. So yeah, I just gave you guys a quick whip around tour, starting from some first principles in quantum mechanics that I taught in the last workshop with this wave function, all the way to the end here. With quantum error correction and this race between all these different models of qubits and these different models of computation, and I just really want to emphasize that there's so much more to the world of quantum computing than just whatever IBM decides is king or whatever Intel comes up with. And yes, Intel does have quantum computing research going on, but they're a lot more secretive about it than IBM is. From what I've read, IBM's goal by making their computers openly accessible and sort of shelling out all this money for it is they will definitely reap losses now, but they hope to sort of solidify their brand name as like, okay, number one for quantum computing. But I digress. Before I go into the gates that I promised, this is just a very sort of, I wanted to give a wide eye or a bird's eye view of what the quantum landscape is like right now. If there are any questions, I'll sort of open the floor up for the next 2 to 3 minutes before I transition back into something a little more solid. Terra firma, which would be those single gates that I promised.
Can you make gates on an adiabatic quantum computer?
Okay. Samarth makes an excellent question there. So I mentioned, there is a bit of an equivalence, or there's mathematical proof that there is some equivalence between the gate model and the adiabatic model. As of now, I guess the last time I checked, Samarth, correct me if I'm wrong, but the last time I checked, this was not, or that you can have certain quantum gates represented from the gate model onto the adiabatic model. It is possible, but you're missing the ability. There's like a key gate you need to have like universal one-to-one that's missing. Is that right, Samarth?
Yeah, pretty much. I mean, I've tried making a C naught like gate, which wherein like one quantum bit is controlling another quantum bit, and the value of one is basically the value of the other. And it was not the greatest. I think the biggest problem just being that on adiabatic they don't have the hardware to tell you what the states are like for every single quantum bit. Like it's good for solving the problem, but it doesn't tell you like actual hardware specific like current and information for you to know, okay, like this is actually acting as a solid C naught for the other. So it's more of a like a tooling problem, a tool set problem. So they could improve that honestly if they wanted to by like adding in those kind of tools, but then that would dramatically increase the price to companies that wanted to use their system, and that's why the pricing right now for the IonQ usage and all those is it's getting better through AWS Bracket. I mean, I'd love to hear from like Amir or anybody else who's maybe experimented with it, like how it is at scale, but it's still pretty expensive. It's still outrageous just because like running each of these devices is super expensive in terms of energy costs, and then development of that is also super expensive right now. But it's available, so you can go and try it out.
Ah, okay. That's good to that's interesting to hear. Amir, have you ever used AWS Bracket? I'm curious. I know it's like a I've heard of it, but I've never used it.
Yeah, I haven't used it primarily because of it being cost prohibitive, um, and because most of where I'm at right now I can do just in a simulator, and IBM still being free with some of their quantum devices. There's just not much of a draw for me to try out Bracket yet.
Gotcha. Okay. Let's see. What was it? What did I want? Okay. Yeah. So Samarth made an excellent point here. An interesting detail is that there has been research into like, okay, let's see if we can represent a kind of quantum gate on the adiabatic model. And if you could, this is particularly interesting because I mentioned, like I would argue one of the motivations to do such a thing is that the qubits in the adiabatic model are, you can scale them to a great degree. If just looking at D-Wave's progress relative to, say, IBM Q or ion Q or any of the other ion trap systems. And the idea here is not that we will, the idea isn't that we're going to take every single quantum gate and somehow find an equivalent expression on an adiabatic computer. In fact, there are a set of gates, I believe they're called Clifford gates, plus some other set of gates. But basically, in quantum computing, it's possible to reduce like all the fancy gates or operations you get to like a single pool of gates. You'll probably need like a Hadamard or a C naught. The C naught is like a 2-qubit gate. So in this example, it's just 1 qubit being operated on, but a CX is 2 qubits. And you can technically translate. If there's some gate like that I don't know the exact operation of, I should be able to approximate its operation using a certain number of gates. So the idea with the D-Wave or adiabatic translation is that we're going to find a really nice set of basis gates that works really well with our adiabatic system, and then we can take any arbitrary quantum circuit and sort of do this conversion. And the ability to do this, this kind of approximation is known as the Solovay-Kitaev theorem. I'll go ahead and write out the whole name of this thing. So Solovay-Kitaev. And I believe this theorem wasn't actually built in the context of quantum computing in the first place. It was more of a geometric property, but it basically says that you can keep approximating towards like let's say a gate that you want. And this is a very, very powerful principle. And it's also a very, very mathematically rigorous principle. And it's something that to this, it takes a great deal of brain grease to kind of understand. But the basic idea is something like this. let's imagine that I have this gate. You don't know what the gate does, but it does some kind of operation. My qubit might start in, say the 0 ket, or ket 0. That'd be the natural terminology, but actually it should be 1. So I start at ket 1, and then it puts it into some kind of arbitrary state here. And but the other quantum computer that I want to use doesn't have this gate. So is it game over? Well, no, not really, because you have to remember that the qubits live in this kind of infinite Hilbert space, and if we represent this on the block sphere, there's sort of like you can have an infinite number of points that qubit could possibly be in, and the idea here is I can find a sequence of gates that will approximate whatever this gate did, and I can get closer and closer to that exact approximation. In fact, I can define, I think, the exact amount of error that I would be willing to accept, given a certain number of basis gates to get there. So we can use Solovay-Kitaev for systems to jump or represent circuits between two different systems without losing all too much, because there are certain gates that are easier to implement in some systems than others. Like, for example, in your quantum, the quantum circuit model, this is common in superconducting systems. You can have, you can have a Hadamard, you can have X, your X gate, or your Y gate, and your sort of S dagger gate. These can all be easily represented in silicon systems, because the reality is these gates don't actually exist as discrete units. They all, especially for IBM, they all fall under a special sort of universal kind of gate. And then the universal gate will take parameters that will rotate or modify the phase of your qubit. But we just, we prefer to think in terms of these, Hadamard, X gate, Clifford gate, solely for the purposes of convenience development. Excuse me, I digress. With that being said, the superconducting model has like all these gates at its fingertips. But other models, like the ion trap systems, they don't really have I would say, an intuitive equivalent right off the bat. In fact, if you look this up, one of the native gates you can implement in an ion trap system is called the Ising gates. Ising XX, ZZ, and I think YY. I think that's an actual Ising gate. These are 2-qubit gates. But we have to use Solovay-Kitaev and some of these base gate transformations to get or to translate between different systems. So this is almost like if you have a cell phone which has like the ARM architecture and your computer runs on x86, you'll need some way to interconvert between the two. And this theorem here, Solovay-Kitaev, guarantees that we can do that, which is very nice to have. And that might come in handy, or that does come in handy when we're, there's movement to try and see if we can get an actual quantum gate represented as an adiabatic problem, which means you either have to know the Hamiltonian and somehow map it onto these systems. And I'm going to put this as a footnote for now. I hope to explore this more thoroughly in subsequent workshops, but the way you express a Hamiltonian on, I don't know if it's every, oh, wow, and Amir put a link to an interesting, I don't think I'll have to check out that paper myself, but for those inclined, I encourage you to take a look at it as well. But the idea with these adiabatic systems I mentioned is you need to set up your energy landscape. And the way you do that is you set up your Hamiltonian, but then what is the mechanism that represents the Hamiltonian? Well, it's based off this idea of the Ising model, which has like these sort of, you can think of these as, traditionally in material sciences, you think of these as magnetic domains. And there's always a bit of like frustration, as it's called. I think that's the actual term, where, ideally you want all the domains, in the same direction. But during the process, there's some sort of thermal energy. Some of these domains will be facing down. And as a result, they kind of have a tendency to want to, they get frustrated with their neighbors. And there's some kind of, the general Hamiltonian of the system is higher in this frustrated instance than it is in this parallel instance where all the magnetic domains are facing in the same way. And the idea is this Ising Hamiltonian, or this 2D Ising Hamiltonian. So this is 1D. This is very easy to solve, but you know, in 2 dimensions, it's a little harder to do. And in 3 dimensions, it becomes incredibly prohibitive. And the Ising model is just frequently cited. It's one of those really beautiful things because in many thermodynamic systems, it's very rare to encounter systems that have explicit solutions. And this is one of those rare systems. But the idea is I can sort of toggle the relationships and the sort of orientations of these domains to set up my Hamiltonian. And that is essentially how the adiabatic systems work. Is you use an Ising Hamiltonian. Ising, yeah, I think that's how you say it. You have to set up an Ising Hamiltonian, and then eventually you will do this process where we adiabatically go from one sort of a very trivial Hamiltonian to the desired problem Hamiltonian. And just to keep in mind, when I say adiabatic and I keep saying slow, it's slow in the context of the problem itself. It's not slow as in like, okay, we have to wait 2 decades for this computation to happen. No, adiabatic has a more nuanced meaning in the realm of physics. But and I mentioned like magnetic domains, so that's like one representation of the Ising Hamiltonian. Although there are other representations that don't require like, okay, like, you know, like the magnetic domains in a sheet of metal. You can have something called a spin glass as well. But that's like some very, that's I think out of bounds for what I'd like to, what I am explaining and what I hope to continue with. But you know, for those interested, this is like another, this is a way or a common way to represent the Hamiltonian that you will sort of adiabatically try to solve. And this is adiabatic quantum computation and quantum annealing. Yeah, those are that's how you express your Hamiltonian. Any more questions before wow, holy, I really went on a I know the promise of this whole workshop was single gates, but I couldn't help myself with just how interestingly varied the quantum landscape is. All right, looks like we have 10 minutes left. I think that'll be that'll give us a pretty decent start here. But okay, let's see if I can find what I'm looking for. Okay, here we go. So I mentioned that I wanted to go over single gates, and you know, I think Amir's been here since I started hosting these workshops in the prior quarter, and that quarter ended on single gates. And I know it seems a bit redundant for me to go over them again, but the idea here is that I will get I'm going to get to algorithms this quarter, so I'll probably breeze over these single gates because the idea that operates, the principles of operation are very simple. It's just the things that they do are a little different, and I have to remind. You know, for any qubit or any system that does quantum computation, you need sort of a 2-level system, or you know, two level system. And in quantum mechanics, we'd like to use a notation. I'm not going to focus too much on this notation now, but it will be. I'll put more emphasis on it in the next workshop, and it's called the Dirac notation. Now it's originally reserved solely for quantum mechanics, but it has a nice analog in quantum computing, and the basic idea with the 2 levels is we want to represent them as some kind of vector. If you're familiar with that block sphere representation, you will note that there are 2 sort of vectors that are, you know, they're in line with each other, which is kind of confusing. In fact, I wanted to clarify that right now. So you will need this 2-level quantum system to perform superposition, and superposition is kind of like your mixture between the ket 0 and ket 1, and you can think of these almost as your analogs of 1s and 0s in standard digital computing. And the way we think of these quantum states is we don't think of them in terms of like a discrete value, but we think of them in terms of a vector. So my 0 vector, or you can think of this as like the default energy, or like the lowest energy level, is represented like this, and then ket 1 is represented as the inverse. So it looks like oh, whoops. Sorry, it looks like this. So these are our two kets, and these kets, the kets represent vectors, and these vectors represent the two basis states in our two levels, our two level quantum system. We need at least two levels to perform any sort of quantum computation. And that idea of superposition. So if I drew the block sphere again, okay, so this we represent our qubit through a vector. Okay, Ryan's got to head out. Thanks for attending, Ryan. I appreciate it. But the idea here with the vector is that I can have it in the middle of the sphere, and in the middle of the sphere is when you know you're in your quantum state. But anytime I'm in line on this y-axis, then I'm in the kind of final state, or in kind of as you measure your qubit or you perform a measurement on it, your state collapses into either one of these two, 1 or 0. And you could argue these are the equivalent of 0 and 1 in terms of our digital computers. And the idea with this two-level system, this abstraction, these vectors, is that I don't have to worry about how my quantum computer operates under the hood. I just know that there are two levels of something, and that they can be I can invoke some kind of superposition amongst them. And the way we look at superposition is something like this. So I can have some part or portion of ket 0 plus some portion of ket 1. Alpha and beta, and these coefficients have a property here that this has to be equal to 1. This is sort of your normalization criteria. If we jump outside of Hilbert space for a minute, then you're going to realize that one of the properties of the Hilbert space is that your wave functions, regardless of how crazy they look or what they seem to do in space, if I take the integral, or if I integrate over this wave function from negative infinity to positive infinity, throughout all of space, it has to sum up to 1. So this is sort of carried over into the quantum realm. So the total sum of my coefficients should be, and these coefficients, mind you, don't have to be purely real. It's very reasonable to have imaginary numbers as well. And that's how you can kind of sneak in phase. So superposition is like one of the things that you can visualize, which allows qubits to hold so much more information than a singular bit. But with just superposition itself, let's imagine I made this quantum computer and there's just superposition. The block sphere is a block circle. That's how you would imagine it. It's just superposition. But then that's if I imagine alpha and beta to only be real values. So my superposition would be constrained. Superposition, excuse me, I'm getting a little tongue twisted there. It would be fixed to this one circle, the edges of the circle. But if I add imaginary values, then my other dimension comes in, and now I can have phase, and I can rotate along this sphere like a happy bumblebee of sorts, and I'm a happy camper. So these coefficients can be imaginary, from what I remember. Yes, they are. I'm just double checking with myself here. Now with this being said, once again, we don't care about what exactly 0 or how exactly 0 and 1 are represented. We might be using an IBM system, in which case it's 2 energy levels. We might be using IonQ, which might be using the spins of 2 particles, or we might be using something else. So that's just nice to know. And this constraint that all of these coefficients have to equal 1 is a byproduct of having to stay in Hilbert space. Now, that being said, I mentioned this idea of gates. So the idea behind a gate is that you take your qubit state, you feed it through some like this black box. I'll call it a black box for now. And as a result, your qubit state is now changed in some way. And the way we accomplished this before we dealt with vectors was you had an operator. So if I had some function here, or my wave function, and you have to remember that going between the wave function to Hilbert space, our wave function sort of becomes this vector. I apply some kind of operator, like the Hamiltonian operator. And what happens is I'm going to get the certain discrete energy levels, or it will. I can get some information on my qubit, or I can change the state of my qubit, which is exactly what I intend to do. So your gates in the gate model are analogs to the operators that you'll see in Hilbert space and in quantum mechanics. And you'll notice that, okay, so if my qubit state can be represented as a vector, then to change vectors, normally, you can do scaling or rotations. We use matrices. So it's just a very simple idea of using a matrix multiplication to kind of represent these operators. So for a vector just like it only has like 2 row entries, then we're just going to use a 4x4 matrix here, and all you do is you do matrix multiplication, and you will get another vector out of it. And for single qubits, you can use the block sphere to visualize everything. But when you start getting to 2 qubits and 3 qubits, it's not really feasible. If you do some digging around, there have been attempts to try and find a way to represent 2 qubits nicely, but none of them have really garnered a lot of mainstream focus. And the reason being is that many, like real computer or quantum computationalists, quantum computer scientists don't rely on the block sphere all the time to debug or monitor their work. Instead, they opt to they will opt to stay in this representation, and it's just purely numbers at that point. And then from there, you should already have a hunch as to what state your qubits are in. And the hope of all these workshops and your attendance is that we will get to that point slowly but surely, where you will no longer need a singular sphere or these cute diagrams. No. Anything. I always joke that mathematicians, it's not so much the beauty from a diagram or it's all in the numbers. They can all see it in the numbers. That's exactly what we hope to get you guys towards. But I digress. Let me go ahead and stop sharing this OneNote thing, and I'm going to go ahead and share the other screen that I have. And let's see. Go to Google Chrome here. Okay, and it looks like we're getting tight in time, but there are a large number of gates that can perform these kind of qubit manipulations. Like these X, Y, and Z gates here, all they do is they perform rotations along the axes of our block sphere. So like the X gate, you can think of as the equivalent of a NOT gate, where if I'm in the ket 0, it brings me to ket 1, and vice versa. Of course, that doesn't mean I have to apply it while it's in this sort of in this position. I could easily apply it while the vector is pointed maybe towards the upper right corner or towards the lower left, or maybe there's some phase introduced. There's a great degree of flexibility of what you can do. And X, Y, and Z are they have very intuitive geometrical analogies. But the Hadamard gate is what we really want to focus on, because there's this idea of qubit phase, and we can use phase to encode information, but how do we really jump back and forth between encoding and decoding information via phase? Well, your Hadamard gate is your go-to ticket. And I think I'll save the rest of the explanation of the Hadamard. Like I really, really wanted to get to a super in-depth look at the Hadamard and its role in other quantum algorithms. So you will definitely get to see, or you'll get your taster in the next workshop. I guarantee it. And I know the title of this workshop was emphasis on single gates, but it turns out there was just I did take a large detour into this bird's eye view of the quantum computing realm, but that's only because I just want to make sure that all of you are very well aware that the quantum computing space is incredibly diverse, and we are not just restricted to gate-based computation. All right. So with that being said, looks like we've hit our hour. Do we have any? Are there any questions? I'd love to field anything before anyone has to go. And if you do have to go, then I wish you a wonderful weekend. Amir, I feel like this was a lot of review for you. I apologize if I went a little faster than normal.
No, this is great. Thank you. Always appreciate review as well, just to fill in any holes in my understanding. The thing that I learned that was new today was when you were talking about the wave function and how if you integrated it from negative infinity to infinity, you would have 1.
Ah, yeah. Well, okay. I played a little loose
Okay.
with that. Let me. It's a minor correction to that. Actually, the wave function. So the wave function has an output that is imaginary, right? But in the real world, you don't get imaginary measurements. Everything has some kind of real value. So for that property that I just mentioned, it has to be what we call square integrable. So square integrable. So what really happens is the full definition of what I just showed should have been this. We take the magnitude and you square it, and then you take the integral. This should equal 1. And this is a constraint imposed upon all wave functions in existence. Yeah, that's what I meant. I was a little, I kind of waved my hand at the fact that you take the magnitude and square it. But
Okay.
I'm glad that's something new you picked up. And it's just the rule of thumb, in physics is like you will never measure some value. Like imagine if I told you, like you asked me what the temperature outside was, and I told you, oh well, it's pretty chilly. It's 0 minus 2i. It has no physical significance. But if I apply an operator, if I were to, the operators will give us real values. And from those real values, those are physical observables. So that particular one where I took the magnitude and I squared it, that gives you the probability density of where the particle may be. So you integrate that. So throughout all of space, that should equal 1. Because if I were to scour all of space for this wave function, there is a guaranteed chance I'm going to run into that particle. So that's the sort of full definition there.
Yeah, thanks. Yeah, of course. Well, with adding the I didn't know that it was connected to its probability density. But yeah, of course, any probability function needs to, or any probability distribution has to integrate to 1.
Right.
Yeah.
Right. Yeah. I also that's actually you touched on the other way I like to explain this. If I'm in a hurry and I don't want to bother with the sort of quantum mechanics origin, I just sort of throw my hat in and say, oh well, in statistics it just makes sense that everything adds to 1. So quantum mechanics is an inherently statistical field, so they decided to adhere to that phenomena. That's also another reasonable argument, and much faster to explain than trying to explain why physicists don't like imaginary numbers in the real world.
All right, I'm gonna hop off now, but thank you. Enjoy your weekend.
All right, thank you so
Everyone.
much. Hopefully you'll
Thanks
be
for
able to
coming on.
make it to the next one where I will touch on algorithms after so long.
Yeah, I hope so. Thanks.
All
Thanks
right.
for coming.
Yeah.
Yeah, thank you so much.
See you all.
See ya.
See ya.
Yeah.